In part 5 of further vectors, so travelling along our red u plus v vector here, we're going to be looking at how we can describe motion with vectors. And this will nicely launch us into projectile motion in part 6. But let's get into part 5, motion and vectors. And first we'll just start off by looking at a regular vector. Let's call it vector u. And keeping things general, let's just say that we've moved x in the x direction and y in the y direction, so that our vector u has coordinates x, y. Or if we wanted to write it like this, x times the unit vector I plus y times the unit vector j, which would go this way. But we also know that we can look at the magnitude. So for this diagram, let's say that the magnitude is r, and the angle or the direction of our vector, and that's the angle that it makes with the positive x-axis. So we'll call that theta. So using some right-angled trig, we can see that cos of this angle theta is the adjacent side over the hypotenuse, and so rearranging we can get an expression for x, which is r cos theta. Likewise, if we consider sine of the angle theta, we're dealing with the opposite and the hypotenuse, and we can get y is equal to r sine theta. So this means our vector u can be expressed as r cos theta for the x component and r sine theta for the y component. So now our vector u is expressed solely in terms of its magnitude and its direction. Alright, let's have a go at our first example using this kind of notation. A body experiences an acceleration of negative 10 meters per second in a direction of 135 degrees. We need to find the vector for the acceleration of this body. So what do we know? We know the magnitude. So going with r for the magnitude, that's negative 10, with the units, meters per second. And we also know our angle, our theta, which is 135 degrees. Alright, we are after the acceleration vector, so let's call that vector A. And so what we just talked about was that a vector can be described in terms of its magnitude, which we have, and its direction, which we also have. So this means that our vector A is equal to r cos theta, r sine theta. And so for us, that means we have an r value of negative 10 and a theta value of 135 degrees. Now we don't want to go rushing to the calculator here. We want to use our knowledge of exact values. So we're in quadrant 2 when we consider 135 degrees. And how many degrees is that back from 180? Well, it's 45. So let's consider cos of 45 degrees, and that's 1 on root 2. But cos is negative in quadrant 2. So we have negative 1 on root 2 there. And sine of 45 degrees is also 1 on root 2, but sine is positive in quadrant 2. So we simply have 1 on root 2. Simplifying, so rationalizing the denominator and cancelling out any fractions, well, we notice that this first term is positive, and then 1 on root 2, that can become root 2 on 2. Okay, and so the 10 and the 2 cancel to give us 5 root 2, and then likewise over here, except it's negative. And so we have our final answer, 5 root 2, negative 5 root 2. Now you might be thinking, hang on a sec, isn't this, if we've got a positive x direction and then a negative y direction, isn't this a vector heading down into quadrant 4? Yes, that's right. But initially we thought, hang on, 135 degrees, that's a quadrant 2 angle. Well, notice that because our acceleration magnitude was negative, even though quadrant 2 has us heading in this direction, the negative magnitude means we're pointing back this way. So that's why we've ended up with a vector down in quadrant 4. Alright, let's do our second example. Given displacement vectors u, which is 3i minus 4j, and v, which is negative 2i minus j, find the magnitude and direction of u plus v. So we know that algebraically, when we add vectors, that's quite a simple thing to do. So we have vector u, which is 3i minus 4j, and we're going to add on vector v, which is minus 2i minus j. And so when we consider the like components, we have 3i take away 2i, that's just I, and then we have negative 4j minus j, so negative 5j. So there's our resultant vector. If we think about where this lies, it's 1 across in the x direction, then 5 down, so we're sort of down into quadrant 4. Okay, and so now let's consider, well, let's firstly consider magnitude. Okay, so we know that the magnitude of a vector, that's going to be the square root of its x component squared plus y component squared. Just some basic Pythagoras there, right? So what do we have? We've got 1 in the x direction and negative 5 in the y direction. So 1 squared is 1, 5 squared is 25, and so we have the square root of 26. So that's the magnitude done. Now let's think about direction, keeping in mind that we are going to have quadrant 4, right? So we want the total angle all the way round. Let's come back up to this quick little sketch, right? It's always helpful. We know we've gone 1 across and 5 down. Right, so if we want to consider this angle in here, right, let's call that alpha. We can find that quite easily, and then we'll simply do 360 degrees minus that angle, alpha. Okay, so how do we figure out alpha? Well, looking at the right angle triangle, we're using the opposite and the adjacent, so we've got tan. So tan of alpha will be 5 over 1, which means the angle we're after is inverse tan of 5. When we calculate that, it comes out to be about 79 degrees. Okay, and so it's that 79 degrees that we can then subtract from 360. So going all the way round, right, so all the way round like that, gives us 281 degrees. And so there we have it, both magnitude and direction of this u plus v vector. Alright, moving on now to velocity. And why is velocity different to speed? Well, velocity gives us direction as well as sort of the speed or the magnitude, right? And for that reason, velocity can be thought of as a vector. And so our next couple of examples are going to use velocity as the main focus. So this first one is quite straightforward, but it's worth going through because it nicely matches up with our intuition. So we've got a yacht and we know it's traveling at 80 kilometers per hour. We want to find the resultant speed when, first of all, there's a headwind of 20 k's per hour, and then secondly, when there's a tailwind of 20 k's per hour. So you probably already know what this is straight away, but thinking of it in terms of vectors, let's say we have our yacht vector here, and direction's not so important because we know that the headwind, right, that means that the wind vector is acting in exactly the opposite direction to whatever the direction of the yacht is. So if we want to be technical, we would say that these are unlike parallel vectors. And so hopefully we can see that the overall magnitude or the overall speed is simply going to be the 80 that the yacht was originally traveling at minus the 20, since it's operating in the opposite direction. And so we'll have a resultant speed of 60 kilometers per hour. When we talk about a tailwind, however, the wind is acting in the exact same direction as the yacht. So once again, here's our 80 kilometer per hour yacht vector, and then the wind vector is operating in the same direction, and so our overall resultant speed is going to be the 80 and the 20, which together gives us 100 kilometers per hour. Okay, so hopefully that helps us realize that we can sort of find resultant velocities by adding or subtracting vectors. Let's now look at an example where we take direction into account. A plane is set to fly at 250 kilometers per hour on a bearing of 40 degrees, but there's a westerly wind of 55 kilometers per hour. So we need to find the actual speed and bearing of the plane once we take the wind into account. Now the first thing to note before we get into this is that we are given a bearing, and we are also asked to give our answer as a bearing. And so we just need to be mindful of this, as a bearing is the direction that we take from true north, so from facing north and rotating clockwise, as opposed to the direction of a vector that we've been using as our angle theta, which is taken from the x-axis and going in an anti-clockwise direction. So just something to keep in mind. Also, a westerly wind, just be aware that that means it's coming from the west, right? So it's not heading towards the west. That would be an easterly. So it's coming from the west, which means it's moving left to right across our page. So let's just set up a little bit of a diagram before we start this. So we have our regular XY axes. Let's consider our north direction to be straight up in the Y, and this will be east over in the X direction there. First, let's think about the plane. 250 k's on a bearing of 40 degrees. So 40 degrees, not quite 45, not quite halfway. So something like this is pretty to scale, I think. And we've got 40 degrees in here. Remember, it's a bearing, so start by facing north, which is 0, and rotate clockwise until we hit our 40 degree bearing. And then also we know the magnitude of this is 250. So that's where our plane is heading initially. But then we have our westerly wind. So a vector purely heading from west towards east. And we know that its magnitude is 55 kilometers per hour. And so what's the resultant vector going to look like when the plane is affected by the wind? Well, we know when we add two vectors together, we can put them tip to tail. And so I'm going to move this wind vector up here at the end of the plane vector, and it would, trying to keep the scale, it would go 2 across, and so there is our resultant vector. So let's draw that in. and let's label it as the P plus W vector. Alright, I should probably put the little tilde sign under the P, and running out of room down here. There we go. And under the W. Okay, so we have a bit of an idea of what's going on graphically now. Let's get into the algebra. And so first, focusing on the plane vector. Once again, remember that if this is 40 degrees as a bearing, then our theta is 50 degrees. Right, so theta is going to equal 50 degrees. And clearly we can see that 90 minus 40 is 50. Since we already have the magnitude, we can now express this plane vector as 250 cos of 50 degrees and 250 times sine of 50 degrees. As for the wind vector, well, in the x direction, we have 55, and we could say cos of 0, but that's just 1, so 55. And then likewise, we could say 55 times sine of 0, but we know it has no y direction at all. It's simply the wind in a westerly, from the west to the east. And so we have 55 and 0. So when we add these two vectors together to get our resultant P plus W vector, we can see that we get 250 cos 50 degrees, right, from the plane, plus the 55 from the wind. And then in a y direction, there is no effect, right? It's just what the plane was set at originally, 250 times sine of 50. Right, and that should make sense. Okay, so let's focus on the magnitude first of all. Pythagoras' theorem, the square root of x squared plus y squared. And, it's a bit to write out, but the idea is still the same. The x component is this whole thing, right? So let's write that out. And we'd want to take this x component and square it. And then same with the y component. This part is the y component, 250 sine 50. And we want to square that as well. Once we go and calculate this, and remember, we often now have our calculators set in radians, don't we? So just be aware of that. Change it back to degrees for here. We get approximately 288. So there's our magnitude. Remember as well that our units in this case, when we talk about the speed, is kilometers per hour. But what about its direction? Well, we can use our tan theta equals opposite over adjacent, or y over x. And once again, for our y and our x, they're obviously, relatively long things to write out. 250 sine of 50 degrees over 250 cos 50 plus 55, but the idea is the same. And so we want to take the inverse tan of whatever this is to work out theta, and that's just another calculator job. Once we do that, we get approximately 42 degrees. But remember what the question actually asked us. It didn't ask us for the direction as such in terms of vectors, but rather it asked for the bearing. And so we need to remember that the bearing starts from true north, right? So it's going to be the complementary angle, right? So 42 is in here. That's what we've just found for our resultant P plus W vector. and so therefore the bearing is this one here. So 90 minus 42. When we do that, we get 48 degrees. But writing it with 3 digits, like bearings are written, 048 degrees. And so there we have it. We have the magnitude or the speed of the plane and its bearing after it's been affected by this westerly wind. Now we can also view force as a vector as well, and so it works in a very similar way, in that, if we have some particle or something that's been affected by different forces, those forces are going to have some sort of magnitude, usually in terms of newtons or something like that, but also a direction that the forces are acting. And so just like we treated velocity as a vector, so force can be treated as a vector as well. But we'll leave this video where it is, and yeah, good luck with the exercise questions.